On January 16th, 3i Atlas enters the zero-phase condition, a rare geometric configuration that creates an almost perfect alignment between the Sun-Earth and the object, opening an optimal window for observation. Against this backdrop, the CIA's evasive response to information requests normally reserved for matters of national security has raised suspicions about the existence of a parallel information control mechanism operating alongside NASA's reassuring public statements. These suspicions are further reinforced by data from the Hubble Space Telescope, particularly the presence of a sunward-directed material stream that challenges conventional models of natural comet behaviour. During the zero-phase condition, an opposition surge may occur, producing a nonlinear increase in brightness that allows scientists to infer the microstructure and surface properties of interstellar dust through physical mechanisms such as shadow hiding and coherent backscattering. This phenomenon enables researchers to distinguish between dark carbon-rich material and reflective ice or high albedo surfaces, and to compare the building blocks of other stellar systems with those of our own solar system. The discoveries that follow could reshape our understanding of Atlas and disrupt established scientific frameworks, not only by challenging how interstellar objects are classified, but by forcing a reassessment of the boundary between natural phenomena and possibilities that current science does not yet possess the tools to definitively confirm or rule out. The moment the Freedom of Information request reached the Central Intelligence Agency, the response did not arrive as data, but as silence, and that silence became the first measurable signal surrounding 3 Atlas. The CIA did not confirm records, and the CIA did not deny records which placed 3 Atlas into a category normally reserved for covert satellites, classified operations, and unresolved national security questions. In ordinary circumstances, a natural interstellar object would fall cleanly under astronomical jurisdiction, and NASA would be the only institution expected to speak yet. 3. Atlas quietly crossed an invisible administrative boundary. This response, known as the Glomar reply, is not evidence of intent, but it is evidence of caution, and caution only appears where uncertainty carries consequence. 3. Atlas therefore entered a different analytical space because uncertainty about a rock does not require secrecy, while uncertainty about capability often does. The data itself did not change in that moment, but the way institutions framed 3 Atlas shifted from observation to containment. From a scientific perspective, the Glomar response does not assert that 3 Atlas is artificial, but it does imply that 3 Atlas triggered risk assessment protocols beyond public science. Risk assessment does not ask whether something is likely, but whether its impact would be unacceptable if ignored, and 3 Atlas fits precisely into that narrow logic. Even a 1% probability of an engineered object would outweigh decades of benign comet statistics, because 3 Atlas is not bound by solar origin assumptions. 3. Atlas also arrives during an era shaped by retrospective failure, because intelligence agencies are trained not by success, but by events they failed to predict. When institutions remember missed warnings, silence becomes a defensive structure, and 3 Atlas exists inside that structure without needing to justify itself. No announcement is required and no alarm is sounded because uncertainty is managed by isolation rather than disclosure. The anomaly is therefore not secrecy itself but asymmetry, because 3 Atlas is described publicly as inert, while privately treated as unresolved. That asymmetry produces a gap between narrative and process, and gaps are where hypotheses begin to form naturally. 3 Atlas does not need to be extraordinary to create this gap because classification can arise from geometry timing or incomplete models alone. Still, the Glomar response introduces a quiet question, because rocks do not require hedging language yet. 3 Atlas received exactly that. This question does not accuse, and it does not conclude, but it lingers as an unresolved variable attached to 3 Atlas. As the story moves forward, the silence surrounding 3 Atlas becomes a background constant, shaping how every subsequent observation is weighed. When the Hubble Space Telescope turned its attention toward 3 Atlas, the expectation was modest because natural comets tend to repeat familiar behaviours even when they arrive from distant star systems. Astronomers expected dust drifting away from the Sun, and astronomers expected gas expanding along predictable pressure gradients, because solar radiation defines the direction of release for melting ice. 3. Atlas, however, presented a structure that refused to align with those expectations, and the images revealed a narrow stream extending sunward directly into the force that should have suppressed it. This sunward feature, often called an anti-tail, is not unknown in astronomy, but anti-tails normally arise from perspective effects rather than active emission. In typical cases, dust settles into an orbital plane, and geometry creates an illusion of reversal when viewed from Earth, yet 3I Atlas showed a structure that remained coherent across observations. 3I Atlas displayed a feature that was tightly collimated, sharply bounded and persistently aligned, which is unusual for dust liberated through passive sublimation. The data suggested directionality rather than diffusion, because the material from 3I Atlas did not spread chaotically, as gas normally does when driven by thermal processes. Gas released by melting ice expands isotropically, and sunlight sculpts that expansion afterward, yet 3I at last appeared to initiate motion with intent-like geometry. 3I at last therefore raised an anomaly not of composition, but of behaviour, because the physics of melting does not favour symmetry against pressure. One hypothesis remains conservative because natural processes can produce jets when volatile pockets rupture beneath a crust, and localised outgassing can create focused streams. Another hypothesis stretches further because a focused plume that resists solar pressure resembles exhaust dynamics more than evaporation dynamics. 3 at last occupies the boundary between those explanations where both remain technically possible but unequally comfortable within established models. If the structure were purely sublimation-driven, 3 at last would need an internal architecture capable of channeling flow with remarkable precision. If the structure were exhaust-driven, 3 at last would require an energy source sufficient to maintain coherence against radiation forces. Neither explanation collapses under scrutiny, yet neither resolves the tension created by the geometry 3 at last displays. The anomaly deepens when symmetry is considered because symmetry in nature often emerges statistically, while engineered systems seek symmetry deliberately. 3 at last does not announce purpose, but 3 at last quietly challenges the assumption that randomness dominates small-scale comet behaviour. That challenge does not demand belief, but it demands attention, because models rely on expectation, and expectation failed briefly in this case. As observation continues, the anti-tail of 3I at last remains less a declaration than a question suspended between melting and motion. This question does not resolve itself quickly, and 3I Atlas carries it forward unchanged as the object moves deeper into measured space. Spectroscopic analysis adds another quiet layer to the puzzle surrounding 3 Atlas because light reflected and emitted by 3 Atlas carries information that cannot be shaped by narrative or expectation. When astronomers examined the spectral signatures associated with the dust and gas of 3 Atlas, they found elemental ratios that did not sit comfortably within typical cometary profiles. 3 Atlas showed an unusually elevated presence of nickel relative to iron, a ratio that immediately drew attention, not because it was impossible, but because it was uncommon. In most natural environments, iron and nickel co-form under specific conditions tied to stellar nucleosynthesis and planetary differentiation. Comets, which are considered primitive leftovers, usually preserve those ratios in a way that reflects early solar system chemistry. 3 Atlas diverged from that expectation just enough to register as an anomaly rather than noise. One conservative explanation suggests that 3 Atlas may originate from a parent system with a different metallic history. Stars form from clouds with varying compositions and planets. Asteroids and comets inherit those differences. From this perspective, 3 Atlas could simply be a messenger from a chemically unusual region of the galaxy. A second interpretation introduces a more speculative frame, because high nickel concentrations are familiar not only in astrophysics but in metallurgy. Nickel-rich alloys are valued in industrial contexts for their resistance to heat radiation and structural fatigue. When viewed through that lens, the spectral data from 3 Atlas echoes materials chosen deliberately rather than assembled passively. This does not imply function, and it does not imply design, but it does introduce a mismatch between expectation and observation. 3I Atlas does not behave like a refined object yet. 3 Atlas does not fully resemble unprocessed debris either. The anomaly exists in the ratio itself, not in a dramatic signature, which makes it easy to overlook and difficult to dismiss. If the nickel were evenly distributed, it could reflect internal mixing processes unknown to current models. If the nickel were concentrated near the surface, it would raise questions about exposure erosion or selective loss. 3 Atlas does not reveal which scenario applies because spectroscopy describes presence, not structure. As with other signals associated with 3 Atlas, the alloy ratio does not declare meaning. Instead, the alloy ratio acts as a quiet marker, suggesting that the material history of 3 Atlas may be more complex than that of an ordinary comet. The trajectory of 3 Atlas introduces a subtle but important deviation from what astronomers usually expect from interstellar visitors. Most objects arriving from beyond the solar system approach from arbitrary angles slicing through planetary space, with little regard for the flattened disk in which the planets reside. 3 Atlas, by contrast, follows a path that lies remarkably close to the ecliptic plane, the same geometric stage on which Earth, Mars, and the other planets perform their orbits. This alignment is not impossible, yet statistical models suggest it is uncommon, because random interstellar trajectories favour steep inclinations rather than shallow ones. When 3 Atlas entered the inner solar system, its inclination remained within only a few degrees of the planetary plane, a region astronomers associate with long-term observational advantage. 3 Atlas therefore appeared not merely as a passerby, but as an object positioned where visibility is maximised. From a purely natural perspective, this configuration can still be explained by chance, because probability does not forbid coincidence. However, probability becomes more interesting when coincidence aligns with function, and the function of the ecliptic is observation. 3. Atlas moves through a corridor where every major planet can be seen in sequence, each one crossing the Sun from a privileged vantage point. This geometry matters because planetary transits reveal information unavailable from other angles. When a planet passes in front of a star, its atmosphere filters starlight encoding chemical signatures that distant observers can measure. 3 Atlas occupies a line of sight where such transits occur naturally and repeatedly. If 3 Atlas were a passive object, this alignment would be a curiosity without consequence. If 3 Atlas were an observing platform, the same alignment would represent efficiency rather than accident. 3 Atlas does not announce its purpose, but its path suggests an awareness of where information density is highest. Even without invoking intention, the ecliptic alignment of 3 Atlas complicates simple classification. Natural comets are shaped by gravitational scattering, not by observational optimization, yet 3 Atlas appears optimized by circumstance alone. This does not confirm design, but it weakens the assumption that trajectory carries no informational weight. As 3 Atlas continues its passage, the ecliptic plane serves as a quiet reminder that position can be as meaningful as composition. Whether coincidence or calculation, the observational geometry of 3 Atlas remains an unresolved variable drifting forward with the object itself. As 3 Atlas approached the outer regions of the solar system, its projected path began to intersect with the gravitational domain of Jupiter, a region defined not by surfaces but by influence. Jupiter commands a vast hill sphere, an invisible boundary where its gravity overtakes the Sun's, and any object entering this region experiences a subtle but measurable change in motion. 3 Atlas was calculated to cross this boundary in mid-March, a routine event for passing debris, yet the geometry of what followed drew careful attention. Within Jupiter's immense sphere of control, countless small moons trace irregular paths, remnants of ancient captures and collisions that form a loose dynamic family. Among these bodies is Euphemy, a minor moon only a few kilometers across orbiting at a great distance, where stability is fragile and perturbations are common. 3 Atlas, according to trajectory forecasts, would pass near this specific moon during its transit through the Jovian system. The proximity itself does not violate physics because space is large and intersections occur, but scale matters when probability is considered. Euphemy occupies an extremely small cross-sectional area relative to the volume of Jupiter's gravitational reach, making random close approaches statistically rare. 3 Atlas therefore appeared to be threading a narrow corridor within a vast gravitational landscape. From a conservative standpoint, gravitational focusing can slightly increase encounter likelihood, especially when trajectories align temporarily. Jupiter's mass bends paths, and small moons ride within that distortion, occasionally finding themselves near passing objects. 3 Atlas could simply be participating in that chaotic dance guided by equations rather than intention. Yet the timing remains notable because 3 Atlas does not merely graze the Jovian system, but passes during a window where observational geometry is favourable. The relative velocity of 3 Atlas is high, and its path is well constrained, meaning predictions carry low uncertainty. 3A Atlas does not wander loosely through Jupiter's domain, but follows a precise arc that can be calculated far in advance. In speculative terms, such precision invites alternative interpretations without demanding them. A deliberate flyby would allow sampling deployment or calibration, using Jupiter's magnetic field and satellite system as reference points. 3 Atlas, if purely natural, would gain nothing from Euphemie's presence, yet the encounter occurs regardless. What matters most is not whether the meeting is purposeful, but that it exists as a defined event rather than a diffuse possibility. 3 I at last converts abstract motion into a scheduled moment, one that can be observed, measured and revisited after it passes. Euphemie does not signal, and 3 at last does not slow, but the convergence creates a quiet focal point in an otherwise empty region of space. As March approaches, the path of 3 at last remains unchanged, carrying it toward Jupiter's distant outskirts and past Euphemie's fragile orbit. Whether coincidence or calculation, the encounter stands as a marker in time, a point where motion briefly aligns before continuing outward. The mechanics of orbital capture introduce a demanding constraint because gravity alone cannot easily transform a fast interstellar passage into a bound orbit. When 3 at last enters the Jovian system, 3 at last carries a relative velocity measured at tens of kilometers per second, far exceeding the speeds associated with natural satellite capture. Jupiter can bend trajectories, but Jupiter cannot absorb energy, and without energy loss, objects like 3I Atlas simply pass through and continue onward. In classical celestial mechanics, capture requires dissipation, such as atmospheric drag collision or multi-body interactions that redistribute momentum. For small moons, these mechanisms operated early in the solar system when gas was abundant and orbits were chaotic. 3I Atlas arrives long after that era, in a system that is dynamically settled and largely empty of capture aids. This is where the hypothesis of a kick emerges not as an assertion, but as a boundary condition imposed by physics. If any fragment associated with 3 Atlas were to appear in a stable Jovian orbit after the encounter, that fragment would require a sudden reduction in velocity. 3 Atlas cannot achieve such a reduction through passive breakup, because fragmentation conserves momentum rather than erasing it. Natural disintegration produces debris that continues along similar trajectories, spreading, but not slowing enough to become bound. Calculations show that to be captured, a fragment would need a velocity change comparable to the escape speed of Jupiter itself. 3. I Atlas therefore confronts a mechanical barrier that nature rarely crosses without assistance. The speculative hypothesis proposes that a controlled impulse could overcome this barrier. A brief directed force applied at the correct moment could convert a hyperbolic path into an elliptical one. If 3 Atlas possessed the ability to generate such a force, the Jovian flyby would become an opportunity rather than an obstacle. This hypothesis does not require continuous propulsion, only a precisely timed event. A single impulse applied near closest approach would exploit Jupiter's gravity to amplify its effect. 3 Atlas under this scenario would use physics efficiently rather than forcefully. The testability of this idea gives it weight because it predicts an observable outcome. After the encounter, astronomers would expect to find a new object orbiting Jupiter, one that was not catalogued before. 3I Atlas would leave behind evidence not in words but in orbital data. If no such object appears, the hypothesis weakens without drama. If an object does appear, alternative explanations would struggle to account for the required energy change. 3 Atlas would then be associated with a phenomenon that natural processes cannot easily reproduce. Importantly, this framework does not assume intention, only capability. Capability can exist without purpose, and hypotheses must remain neutral to motivation. 3 Atlas is evaluated not as an agent, but as a system interacting with gravitational constraints. As the Jovian encounter approaches, the kick hypothesis waits quietly because it cannot be argued into existence. 3 Atlas will either pass through unchanged or leave behind an orbital signature that reshapes interpretation. In that moment, theory yields fully to observation, and the motion of 3 Atlas becomes the final arbiter. The concept of a surveillance timeline emerges not from intention, but from geometry, because motion through space defines what can be seen long before purpose is assigned. When orbital models are traced backward, 3 Atlas appears to have entered the outer boundary of the solar system thousands of years ago, drifting inward through regions where subtle signals become detectable. At that distance, 3 at last would not observe planets as bodies, but atmospheres as spectral hints embedded in starlight. As 3 at last crossed into the Oort, Cloud Earth had already transformed its atmosphere through biological activity, and oxygen had accumulated to levels that alter stellar absorption lines. Oxygen is unstable without constant replenishment, and its persistence signals a system far from equilibrium. 3 I Atlas positioned along a slow inward arc would have encountered those signatures long before modern humanity existed. Time deepens the anomaly because as centuries passed, Earth began to change again, and industrial processes introduced new compounds into the atmosphere. By the mid-20th century, synthetic molecules appeared that nature does not produce in abundance, and those molecules left distinct spectral fingerprints. 3 at last, according to reconstructed trajectories, occupied vantage points where such changes would have been visible in principle. The alignment becomes more striking when radio history is considered because the detection of the unexplained WOW signal in 1977 coincided with a line of sight that included 3 I at last. This does not imply causation and coincidence alone cannot carry explanatory weight. Yet 3 I at last occupies that coincidence in a way that connects geometry timing and signal propagation. From a conservative perspective, these overlaps reflect nothing more than chance layered upon chance. The galaxy is vast and alignments inevitably occur without meaning. 3 I Atlas could simply be passing through a region of space rich in human narrative without interacting with it. From a speculative perspective, the same timeline can be read as continuity rather than accident. A long-duration traversal allows repeated sampling rather than a single snapshot, and repetition improves detection reliability. 3 Atlas moving slowly relative to stellar evolution would experience Earth not as a moment but as a process. This idea does not require active monitoring because even passive observation accumulates information over time. Light carries history forward, and 3 I Atlas moves through that history whether it intends to or not. The timeline therefore exists independent of motive shaped entirely by motion and physics. What makes the timeline compelling is not what it claims, but what it permits. 3 I Atlas could have observed nothing of consequence, or 3 Atlas could have observed change unfolding across millennia. Both possibilities remain viable, suspended until interpretation is anchored to evidence rather than alignment alone. The Trojan horse scenario does not begin with deception but with restraint, because restraint is often the first response when options are limited. In this framing, silence is not an admission of knowledge but a method of control. And 3 I Atlas becomes significant not for what is said about it but for what is deliberately withheld. Institutions trained to manage uncertainty often choose stability over transparency, especially when transparency offers no corrective action. 3 at last enters this scenario as a passive catalyst because the object itself does not threaten. Yet the implications surrounding 3 at last introduce a symmetry between awareness and response. If an object cannot be influenced, intercepted, or redirected, public acknowledgement may offer little benefit beyond anxiety. In such cases, classification functions as a psychological barrier rather than a physical one. The Trojan horse analogy does not suggest hidden intent within 3 Atlas, but it highlights the risk of misclassification. In ancient narratives, danger did not arise from the object itself, but from assumptions imposed upon it. 3 Atlas framed as inert passes freely through analytical gates that would otherwise demand scrutiny. From a cautious perspective, maintaining a natural explanation preserves social equilibrium. Markets remain stable, institutions remain trusted, and daily life continues uninterrupted. 3 Atlas in this view becomes a background phenomenon rather than a focal point. However, the cost of this approach is informational delay, because delayed acknowledgement limits collective analysis. Scientific communities thrive on distributed observation, and secrecy concentrates interpretation within narrow channels. 3 Atlas therefore exists at the intersection of governance and knowledge, where control competes with understanding. The scenario grows darker only when powerlessness is introduced. If 3 Atlas were suspected to be more than natural, and if no intervention were possible, silence would function as harm reduction rather than denial. In that case, knowledge would not empower response and response would not alter outcome. 3 Atlas does not require hostility to create this condition. Even a neutral observer passing without engagement could place institutions into a position where acknowledgement offers no advantage. The Trojan horse metaphor then shifts, becoming less about invasion and more about inevitability. Importantly, this scenario remains hypothetical because it rests on compounded assumptions rather than direct evidence. No document confirms such reasoning and no statement admits to calculated silence. 3. I-Atlas therefore occupies a narrative space shaped by inference rather than declaration. What persists is the tension between precaution and openness. 3-Atlas moves forward regardless of interpretation, while institutions choose narratives that minimize disruption. In that divergence, the Trojan horse scenario remains unresolved, not because it is hidden, but because it cannot yet be tested. The approach to a phase angle of 0.69 degrees transforms an abstract trajectory into a physical experiment, because geometry alone can reorganize how light behaves. When at last the Sun and Earth align with such precision, the system briefly becomes a natural laboratory that no spacecraft could realistically construct. 3I does not change its structure during this alignment, yet the conditions around 3I change how information is extracted. In astronomy, phase angle describes how light strikes and returns from a surface, and most objects are observed at angles where shadows dominate interpretation. At 0.69 degrees, shadows collapse, and surfaces reveal properties that remain hidden at larger separations. 3 enters a regime where illumination becomes diagnostic rather than descriptive. This geometry allows scientists to probe microstructure without contact, because photons act as both messengers and instruments. Light emitted by the sun strikes. 3 scatters through dust and surface irregularities and returns directly toward Earth. 3 therefore becomes both subject and medium within the same experiment. The rarity of this alignment adds weight to the observation. Interstellar objects typically pass through the solar system at angles that prevent such near-zero configurations. 3 however, intersects the ecliptic in a way that collapses distance into alignment rather than proximity. From a conservative perspective, this event simply offers better data resolution. Sharper phase angles reduce ambiguity and tighten constraints on models of surface roughness and particle size. 3 benefits incidentally from this clarity without implying intent. From a speculative perspective, the same alignment raises questions about probability and recurrence. An observing platform designed to study planetary systems would benefit from such geometry because it maximizes information yield per unit time. 3 occupies that geometry whether by chance or design, and the distinction cannot be made from alignment alone. What matters is that the alignment converts 3 into a testable system. The brightness response of 3 at 0.69 degrees will follow known physical laws or diverge from them. Either outcome refines understanding rather than ending inquiry. In this configuration, 3 at last is no longer interpreted through analogy with familiar comets. Instead, 3 at last is examined through first principles of light interaction. Geometry replaces assumption, and measurement replaces narrative. As the alignment approaches, anticipation builds quietly, because the experiment requires no action beyond observation. 3I, Atlas will not announce the moment and instruments will not intervene. The laboratory exists only briefly, and when alignment fades, the opportunity closes with it. The reminder of an opposition surge begins softly, because the phenomenon is subtle, until geometry forces it to reveal itself. When the phase angle collapses below 2 degrees, light no longer behaves as a simple reflection, and 3. At last enters a regime where intensity grows faster than intuition expects. This nonlinear increase is not an amplification of brightness alone, but an amplification of information encoded within returning photons. Under ordinary conditions, brightness changes smoothly as distance and angle vary. In the opposition surge regime, however, 3 at last reflects light back toward its source with disproportionate efficiency. 3. I-Atlas therefore becomes brighter not because it moves closer, but because scattering pathways begin to overlap. 2 mechanisms dominate this process and each carries diagnostic weight. The first is shadow hiding, where surface grains conceal their own shadows when illumination aligns with observation. 3 at last under this mechanism would brighten modestly, revealing macroscopic roughness without implying complexity. The second mechanism is coherent, backscattering, where light waves traverse reciprocal paths and interfere constructively. In this case, photons entering the dust environment of 3I Atlas scatter multiple times before exiting along identical routes. 3I Atlas would then produce a sharp spike in brightness, narrow in angle and intense in amplitude. This distinction matters because coherent backscattering requires structure at specific scales. Dust grains must be comparable in size to the wavelength of light, and the medium must allow multiple scattering events. 3. Atlas therefore becomes a probe of its own microstructure through the behavior of reflected light. If the surge is broad and muted, 3 Atlas likely consists of dark absorbent material where photons are lost before interference occurs. If the surge is sharp and pronounced, 3 Atlas would indicate a highly scattering environment, possibly composed of porous aggregates or reflective surfaces. Both outcomes fit within natural physics, yet each points to a different formation history. What makes this event significant is not brightness itself, but timing. 3 Atlas enters the opposition surge window only briefly, and the geometry cannot be repeated once the object departs. 3 Atlas therefore offers a single opportunity to observe nonlinear light behavior under pristine conditions. The anticipation surrounding this moment remains restrained because the experiment requires no interpretation in advance. The light curve of 3I Atlas will either bend sharply or remain smooth, and theory will adjust accordingly. 3I Atlas does not need to surprise because confirmation alone advances understanding. As photons return toward Earth carrying the signature of multiple scatterings, 3I Atlas transforms from a distant traveller into an optical system. The surge, if it appears, will last only moments in astronomical terms. When it fades, 3 Atlas will continue onward, leaving behind a curve of light that quietly records its internal story. Albedo becomes the next interpretive lens because reflectivity determines how light is treated after it reaches a surface. Albedo does not describe colour in a visual sense, but efficiency measuring how much incoming energy is returned rather than absorbed. When scientists speak of albedo, they're asking whether Atlas behaves more like clean snow or dark charcoal under stellar illumination. In the solar system, most comets are surprisingly dark because long exposure to radiation processes organic material into carbon-rich residues. These surfaces absorb light readily, converting photons into heat rather than reflection. If Atlas followed this pattern, its brightness response during the opposition surge would be limited and smooth. A low albedo surface suppresses multiple scattering, because photons vanish into the material after only a few interactions. Under such conditions, shadow hiding dominates, and the surge appears gentle rather than dramatic. Atlas, if dark, would align comfortably with known cometary behavior, even if its origin lies beyond the Sun. The alternative presents a quieter challenge to expectation. High albedo surfaces reflect light efficiently, allowing photons to bounce repeatedly before escaping. If Atlas exhibits a strong narrow brightness spike, reflective material would become difficult to ignore. Clean ice, crystalline frost, or loosely bound aggregates can all produce elevated albedo under the right conditions. Such materials scatter light rather than absorb it, preserving wave coherence across multiple paths. Atlas composed of these materials would reveal an interior that has remained shielded from long-term darkening. This possibility introduces tension, not because it implies artificiality, but because it implies preservation. Interstellar space is harsh and pristine surfaces degrade over time. Atlas maintaining high reflectivity would suggest either youth or protection. From a conservative standpoint, Atlas could be a fragment ejected recently from a distant system carrying fresh ice into interstellar space. Time since ejection matters because radiation damage accumulates slowly but relentlessly. Atlas, under this view, would simply be younger than assumed. From a speculative standpoint, reflective material evokes design choices familiar from engineering. High albedo surfaces manage thermal load and radiation exposure efficiently. Atlas does not need to be engineered to display such traits, yet the parallel exists. The albedo question therefore acts as a discriminator, rather than a verdict. Dark outcomes compress interpretation toward natural processes, while bright outcomes expand interpretive space. Atlas will not announce which category applies because the answer resides in a curve rather than a statement. As measurements accumulate, reflectivity becomes a story told by light returning from Atlas. That story will not declare origin or intention. Instead, the albedo of Atlas will quietly narrow the range of plausible histories, guiding interpretation without forcing conclusion. Polarization offers a different window into structure, because polarization measures not brightness, but the orientation of light after interaction. When sunlight reflects from dust or surfaces, the electric field of the light waves rotates in ways that depend on particle shape and texture. Atlas therefore carries information not only in how bright it becomes, but in how light twists as it leaves at last. Under typical cometry conditions, polarization follows a predictable curve as phase angle decreases. At moderate angles, light shows a negative polarization branch indicating rough, irregular grains, scattering photons unevenly. Atlas, if composed of familiar dust, would follow this curve smoothly as alignment tightens. As phase angle approaches zero, however, some materials produce a reversal or suppression of polarization. This change occurs when scattering paths become highly symmetric and when particle geometry supports coherent interactions. Atlas entering this regime becomes sensitive to grain shape rather than grain chemistry. Data from similar measurements on asteroids and moons show that spherical or compact grains behave differently from elongated or flattened ones. Needle-like particles polarize light asymmetrically, while plate-like grains introduce distinct angular signatures. Atlas, if populated by such exotic shapes, would deviate from standard polarization models. The anomaly arises if polarization does not merely diminish, but inverts unexpectedly. Such behavior would imply that scattering within Atlas involves ordered or repeated pathways uncommon in random aggregates. Atlas would then suggest a dust environment shaped by formation processes not well represented in solar system analogues. From a conservative interpretation, unusual polarization could result from extreme porosity. Highly fluffy fractal aggregates allow light to penetrate deeply and re-emerge with altered orientation. Atlas, under this explanation, would consist of delicately assembled structures formed in low-density environments. From a more speculative angle, ordered particle shapes evoke manufacturing constraints rather than natural fragmentation. Industrial processes often produce consistent geometries because consistency serves function. Atlas does not claim such origin, yet the polarization data would permit the question to exist. Emotion enters quietly at this stage because polarization is not dramatic to observe, yet it is intimate in implication. Light returning from Atlas carries a memory of every surface it touched, and that memory arrives without interpretation. Atlas becomes less an object to be seen, and more a medium that reveals how it is touched by light. The bridge forward lies in correlation rather than conclusion. Polarization measurements will be compared against albedo and opposition surge data to see whether the signals align or conflict. Atlas gains meaning not from any single anomaly, but from how anomalies cluster or dissolve when viewed together. As the phase angle widens again, the polarization window will close. Atlas will move on, carrying its unresolved microstructure with it. The question of exotic grains will remain suspended, not answered, but sharpened by the way light briefly behaved around Atlas. At a phase angle of 0.69 degrees, geometry quietly reverses perspective, and 3i Atlas is no longer only an object being observed, but a location from which observation becomes possible. From the position of 3i Atlas, the Sun-Earth, and 3i Atlas align in a configuration that astronomers recognize as a near-perfect transit geometry. 3i Atlas occupies a vantage point where Earth passes almost directly in front of the Sun, transforming Earth into a silhouette rather than a source. In this configuration, Earth behaves as an exoplanet would to a distant observer, because starlight grazes the upper layers of Earth's atmosphere before continuing outward. 3. Atlas situated along this line would receive light that has been filtered through gases, clouds, and chemical gradients surrounding Earth. 3. Atlas therefore exists at a position where biological and technological signatures could in principle be detected without proximity. Transmission spectroscopy relies on this exact geometry. When light passes through an atmosphere, specific wavelengths are absorbed, leaving patterns that reveal composition. 3 at last aligned with Earth, and the Sun would be exposed to those patterns naturally without instrumentation needing to maneuver. Oxygen and ozone imprint strong absorption features, and their coexistence signals an atmosphere maintained far from equilibrium. Methane adds further complexity because methane does not persist alongside oxygen without continuous replenishment. 3 at last, if equipped to analyze spectra, would encounter evidence not of habitability alone, but of active processes reshaping Earth's air. The significance deepens with the presence of industrial compounds. Chlorofluorocarbons and similar molecules do not arise from geological cycles in meaningful quantities. 3. Atlas positioned along the transit line would receive light altered by compounds that encode technological activity rather than biology alone. This scenario does not assert that observation occurs, it simply establishes that geometry permits observation, and geometry exists independently of intention. 3. Atlas does not need to be a sensor to occupy a sensor-friendly position. Emotion enters subtly here because the symmetry is difficult to ignore. While humans analyze dust light and motion associated with 3 at last, the same alignment allows Earth to be analyzed in return. 3 at last becomes a mirror not by design, but by circumstance. From a conservative viewpoint, this reciprocity is irrelevant because no evidence confirms instrumentation or reception. From a speculative viewpoint, the alignment feels efficient because it maximizes information transfer in both directions simultaneously. 3. Atlas sits at the intersection of those interpretations, neither confirming nor denying relevance. The transition forward lies in humility rather than alarm. Earth has long been detectable in principle regardless of 3 Atlas because light travels without regard for audience. 3 Atlas simply reminds observers that observation is rarely one-sided. As alignment fades, Earth will return to being a point of light rather than a transiting world. 3 Atlas will continue outward, carrying no message and leaving no reply. What remains is the quiet recognition that for a brief moment geometry allowed Earth to be seen as clearly as Earth sees 3 Atlas. Industrial confirmation enters the discussion through chemistry, rather than speculation, because certain molecules carry meanings that biology alone cannot produce. When Earth's atmosphere is viewed through transmission, geometry, specific absorption lines emerge that correspond to compounds synthesized intentionally by technological processes. Atlas positioned along the transit line would encounter sunlight altered by these compounds, as a matter of physics rather than intention. Chlorofluorocarbons represent one of the clearest examples of such markers, because chlorofluorocarbons do not arise naturally in stable abundance. These molecules require controlled reactions, industrial temperatures, and manufactured precursors that geology does not supply at scale. Atlas would therefore receive a spectral signal that cannot be confused with volcanic output or biological metabolism. Unlike oxygen or methane, chlorofluorocarbons persist without biological feedback loops. Once released, chlorofluorocarbons remain detectable for decades, accumulating as a record of industrial behavior rather than life itself. Atlas encountering these signatures would not need to interpret motive-only presence. The significance lies in specificity, because few molecules encode intent so clearly through their absence in natural systems. Chlorofluorocarbons function as technomarkers, precisely because they betray process rather than survival. Atlas exposed to such markers would receive evidence of engineering without requiring proximity or interaction. From a conservative standpoint, this scenario remains theoretical, because detection requires sensitive instrumentation and favourable signal-to-noise ratios. Distance dilutes signal strength and stellar interference complicates extraction. Atlas may simply pass through the alignment without recording anything at all. From a speculative standpoint, even partial detection would carry disproportionate meaning. A weak but unambiguous technomarker would distinguish Earth from worlds shaped only by chemistry and biology. Atlas, under such conditions, would encounter a planet defined not only by life but by alteration. Emotion enters not through fear but through recognition. Human activity has reached a scale where atmospheric composition records decision rather than accident. Atlas does not judge those decisions, but Atlas would witness their trace if observation occurred. The presence of chlorofluorocarbons also reframes time. These molecules mark a narrow window in Earth's history, a brief industrial phase, rather than a planetary constant. Atlas encountering that window would encounter humanity not as a species but as a moment. This framing avoids agency and intent because chemistry does not imply response. Light carries information outward regardless of who receives it. Atlas simply occupies a place where that information converges. As the alignment relaxes, the opportunity for such detection diminishes. Earth's atmosphere will continue to evolve and chlorofluorocarbons will decay or be replaced. Atlas will move on, leaving behind the question of whether industrial confirmation requires an observer to exist. The retrograde motion of 3I, Atlas introduces a final geometric curiosity, because moving against the prevailing flow of planetary orbits reshapes what can be seen and when. Most bodies in the solar system share a common direction inherited from the disk that formed them, and this shared motion simplifies encounters and limits viewing angles. 3 at last, however, travels opposite to that flow crossing the system, like a countercurrent rather than a participant. This reversal matters because relative motion stretches observation time. When an object moves with the planets, encounters are brief and alignment windows close quickly. 3. Atlas moving against the stream prolongs intersections with transit zones, where planets repeatedly pass between star and observer. 3. Atlas therefore remains within information-rich corridors longer than a prograde visitor would. From a natural perspective, retrograde orbits are not forbidden. Gravitational scattering among stars can invert trajectories, and interstellar space does not preserve preferred directions.